All right, good morning. Okay, well, let's look at today's data set. Today we're going to look at the MNIST handwritten digits data set as an application of neural networks. Oh, by the way, we graded your midterm exams and scores have been posted. So I don't return exams, but if you have any questions about the exam or how you did, or you want to see what you got wrong, come by office hours. I'm happy to let you see your exam. I'm happy to show you the answers, answer any questions you have. So, okay, but let's talk about the MNIST handwritten digits data set. And so to do this, let me do 3 blue, 1 brown on neural networks. All right, so this is the video. Okay, actually, I don't want to play this just yet.
When it comes to travel insurance, what's
okay, I want to mute that. And then let me also just show you what the MNIST data set looks like. We wanted to show images. Okay, so the MNIST data set is a bunch of handwritten digits images of handwritten digits. Okay. And so this comes, you know, I guess this application is, I don't know, close to 30, 40 years old now, but this is kind of a nice clean data set that we can use to kind of get us into this first introduction of, I guess, image recognition, right? And so it was, you know, the problem kind of originated with like at the post office, and it used to be if you hand wrote the address on a letter, okay, and you put it in the mail, then somebody would have to look at that and they would have to sort it by hand. They would look at it and they would say, okay, that looks like somebody wrote the zip code, you know, 90210, and then that would go over to, and they would sort it into different piles. And they said, you know, this is slow. Can we speed this up with machines? And so they wanted, you know, the computer to be able to read someone's handwriting and then figure out what the corresponding zip code was. The problem is, of course, is that everyone's handwriting is a little bit different, and our brains are able to look at these things and recognize, okay, these are all the number 2, even though they all look very different. And so somebody had to go through, scan all of these things, and crop them down, and do all of these things and center the image. And so that's what the data set consists of. It's very, very clean in that every single image, you know, the number is like perfectly centered, okay? And so even though, you know, the numbers themselves are all written very differently, we know what every one of these numbers are, and every one is kind of centered and very clean in that way, right? And then they're also all labeled correctly in that, you know, we even though this is kind of hard to read, we know it's the number 2 because whoever input the data, you know, they could see like this one is going to Beverly Hills, and we know the zip code for Beverly Hills is 90210 or whatever, and therefore we know that this digit, even if it looks kind of crazy, we know that this is a 2 type of thing. Okay, so so the digits are all written in there. So every image is 28 pixels by 28 pixels. So this really, really kind of tiny image, but it's enough information for us to show a picture. Okay. And it's a black and white image. And so the numbers, so if you think about what an image really is, this is a 28 by 28 image, which is really just a 28 by 28 matrix, okay? And there's a number in each of those kind of spots that corresponds to whether the pixel is white or black or some shade of gray in between. I believe they're on 256 levels, so it goes from 0 to 255. So I think, in this image, 0 would be a white pixel, 255 would be a black pixel, 120 would be something like gray. Okay. In this video, he has scaled them to be between 0 and 1, and then he's reversed the coloring so that the ink is in white and the background is in black. Okay, so 0 would be black, and then 1.0 would indicate something, I guess, to indicate the colored in at white over here. Let me so this is 3 blue 1 browns, but what is a neural network? I'm going to pause the video recording, and so if you're watching the video recording, look this video up, scroll to around, I don't know, 3.5 minutes or so. I mean, watch the whole video, but the relevant segment is around this time. And the reason why I'm pausing the recording is because if you play someone else's video in your own video, you get hit with like copyright strikes on YouTube. So we're gonna just pause the recording here. And so what this video kind of shows us is that each image comes in. You're gonna have this 28 by 28 grid of pixels that just gets kind of stretched out into this one input layer with 784 values, right? So in our kind of example neural network that we had kind of 2 values in the input layer, 3 values in the hidden layer, 1 value in the output layer. Okay, in this structure, Grant, author of 3 blue 1 brown, has 784 nodes in the input layer. He arbitrarily chose to have 2 hidden layers with 16 nodes inside, and we have 10 nodes in the output layer. I think for our example that we're going to run in the class, I think I've chose 1 hidden layer, I think with 30 nodes. We'll have to double check what it is, okay? But anyway, the important thing is that, well, I guess the things that we don't have, we can't alter would be that the input layer is going to have 784 nodes because we have 784 pixels. So we need 1 node for every pixel coming in. And then the output layer is going to have 10 nodes, okay? In this case, we're going to have a node corresponding to each possible classification, a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, okay? In this image, the image is a 7, so what we want to see in the output layer is that the nodes corresponding to all the digits other than 7 have values that are 0 or very close to 0, and then the node corresponding to the 7 has a value that's close to 1, okay? This is how we're going to have the data show up, and we're going to, quote, train the network, basically pick all of the different weights that go into all of the connections, and we're going to say, this is what we want you to produce. And we're going to say, we're going to calculate a penalty when you don't produce this number, right? Even though it's a number between 0 and 1, it's not a probability, okay? It's just 0 if it's low, 1 if it's high, okay? Probabilities have a lot more constraints other than just 0 and 1. Namely, they have to add up to 1. They have to, there's certain properties about probabilities, and these numbers aren't going to obey that, okay? So you can have like a 0.1, a 0.1, a 0.2, a 0, a 0.99, and things that don't add up to 1 and something like that. It's just, we're looking for things that are close to 0 for everything other than the one that we have. We have 10 nodes, 1 corresponding to each digit, because this is a classification problem. We're not able to just use 1 node, okay? If we had 1 node, you might ask, why can't you just use 1 node and have it output a 1 a 2, a 3, a 4, or a 9, or a 0, or whatever digit it is, right? Why can't you just have one node that goes to, say, 7, or one node, and whatever number it outputs is the number that it should be? The reason why is because if you have only one node, the way you measure something is incorrect is you measure how the distance between that value and the true value. Okay, so let's say the true value was the number 9. Okay, if you had only one node, if the true value is a 9 as far as the digit classification goes, it would say if one network guessed the digit 8 and another network guessed the digit 6, okay, it would say the 8 is less wrong than the 6 as far as guessing the digit, okay? Which makes sense if you're trying to predict like money, okay? How much money are you going to make? 8 is a better guess than 6. That is true. However, when it comes to classifying digits, 8 is equally wrong as guessing 6, okay? And it's not how right or wrong you are. There's not different degrees of right or wrong as far as correctly identifying the digit, okay? Correctly identifying the digit, you either got it right or you got it wrong. And there's no saying like 8 is a better guess than the number 6 or something like that, okay? As far as guessing numbers go, sure, 8 is closer to 9 than 6 is, but guessing digits, these are categories, really, okay? Even though they look like numbers, they are categorical classifications. So, so that's how it's going to go, okay? So in order for us to get the data, I have a couple links, and students in the past said, so I have all of my R code written right here. You can download those R scripts. And then you can, sometimes this data set or sometimes this link works, and then sometimes it doesn't work. So I don't know, it's working for me. I can go to this website, yan.likun.com, and I can download the 4 files right here, okay? If you can't, there is a mirror setup that you can kind of get from Amazon, and the 4 files are right here as well. You can download them. When you download them, I strongly recommend creating a folder. Maybe create a folder where you're going to have the scripts, and then inside that have another folder called MNIST where you're going to put in the data files. Okay. And then when you download them, they come in as .gz files. These are, I guess, gzip files, and you have to unzip them. If you're on Mac, you'll go to navigate to that folder in Terminal, and you'll type in gunzip, okay, and then the name of the file. And you have to do this 4 times. There's 4 different files, and so you have to gunzip all 4 of them. If you're on Windows, I would say install this program 7-zip, and this is a free program that you can use to unzip different kinds of files, and it's good. It's open source. You're not going to get a virus or something like that. Okay, so that's and then you'll unzip them into your folder here. Okay, and then there's a script that we can run to load up this MNIST data. And so there's 2 functions, and one will be we'll call load. MNIST. Hang on. Okay. It'll take a little bit of time to load these, I think. Okay. So in my environment, I now have, so I loaded the, I called the scripts, so these scripts will kind of read in the MNIST data files, which I think are, I don't know what format they're in, but they're a little bit hard to read. They're, I think, in binary format, but we can read them into a form that R can understand. So what I'm going to do is the text big enough on the screen for you guys to be able to read and stuff? Oh, okay. And you know what? Let me give you view quiz answer. Week 4 Friday. Okay, first view quiz answer is C. C as in cat. C is your first view quiz answer. All right, let's go ahead and take a look at our first digit. So you could see train and test. This is these are kind of these big lists here, right? And in train, there is there's the X and there's the Y. X is the input and Y is the label. So X is, there's 60,000 images in the training data, okay? And so each row is one image, okay? And each row has 784 values because we took that 28 by 28 and we just kind of unstacked them into just one long vector of 784 values. So each row, there's 60,000 rows, one corresponding to each image, and so we have that. So let's just kind of look at the first image, and the corresponding label is going to be a 5. Okay, so this is the label, and the digit is stored as just kind of this vector of 784 values. All right, and so you can see we have a whole bunch of zeros, and then the 150 third value is a 3, then an 18, 18, 18, 126, and so on and so forth. I have there's another script here, a little function that will take the array that's 784, or take the vector 784 values long, arrange it into a 28 by 28 grid, and then create a plot of the resulting grid. And so I'll go ahead and run that, and this is what the image looks like. And we could say, okay, sure, that looks like the number 5. Okay. What we need is we need to turn the label from the number 5 into basically the output nodes. Okay, so I'm going to create 10 values, and the one that corresponds to a 5, which will be our 6th column, will get a 1. Okay, because it's going to start at 0 and end at 9. The 10th column will be 9. So I'll turn that label into a vector, and so you can see this first image. We have this is going to be the correct result. We want zeros for all of the nodes, a 1 for the node that corresponds to a 5, and a 0 for all of the other nodes. Okay, this next digit here, the second image, has a 1 in the very first column, which corresponds to a 0, and zeros everywhere else. And so we can kind of just say, hey, you know what? I just want to say is, let's look at the second row, and that looks like a 0. Okay, and I think the image in the data set that we saw in the video, this number 9 is exactly this number 9 that we have here. Okay, and so we're working off of the same data set, and basically what we want to do is we want to set up a neural network that's going to be able to look at these 784 values and say this is the number 9. Okay, something in our brain is able to look at this two-dimensional image and have character recognition, and we recognize that this is a 9, the computer has to do something. It doesn't have our eyes, but we're just going to give it 784 values, and we're going to say this, whatever this is a 9, okay? So here, these are the functions. These are the same functions from earlier. We put in our sigmoid function. We put in the derivative sigmoid prime. My cost function is going to be how I'm going to calculate the difference between the actual values and the predicted values, okay? So our the outputs are all length 10. The true values are going to be 0, 0, 0, 1, 0, 0, 0, or something like that. Whereas the predicted values, the y-hats, will be something like 0.01, 0.1, 0.02, something, a whole bunch of decimal values between 0 and 1. And we're hoping that, that the corresponding value is going to be close to it. So I'm going to say input layer, 784 values. Output layer has 10 values. And here in my network, I'm going to keep it simple, and we're going to just have one hidden layer with 30 nodes in it, okay? 30 nodes in our hidden layer. And so that way I only have 2 weight matrices, the weight matrix from the input layer to the hidden layer, weight matrix from the hidden layer to the output layer, okay? Versus, you know, in this one, you have 3 weight matrices, right? This is a weight matrix between of all of the connections here. You have a weight matrix here for all the connections here, and another weight matrix here for all the connections, which is totally fine, but it would require us to do some more derivative calculation, gradient calculation. So just to kind of avoid that, we're going to just keep our network structure very simple here. Okay, so I have 2 weight matrices, W1. The dimensions of W1, our first weight matrix, will be 784 by 30. Okay, and I'm going to generate a bunch of random uniform values. RUnif generates values between 0 and 1, and I'm going to just slide those over 0.5 to the left. And that means this will generate values between negative 0.5 and positive 0.5. Okay, and then W2 is going to have 30 by 10, 300 values in that matrix. And again, I'm going to just generate some random values to start off with, and I'm going to slide them over 0.5, so it goes from negative 0.5 to positive 0.5. Okay, so now if I look at my my environment, we can see W1 784 by 30, W2 is 30 by 10, and we got a bunch of values in there. We are going to do something called stochastic gradient descent, okay? And if we just did regular gradient descent, we would take our input matrix, of which I have 60,000 rows, and I would kind of force that through my network. I would do forward feed, right? You take your input X matrix, 60,000 by 784, multiply it by your W1 matrix, all right, which is 784 by 30. So then your next thing would be 60,000 by 30. And then you take that and you multiply it by your W2 matrix, and you get, which is 30 by 10. So you get 60,000 by 10 as your output. That is just a lot of numbers for a computer to multiply and crunch. And our computer could do it, but it's going to be very slow. So we're going to do, remember, when you calculate the gradient, okay, it ends up being kind of just like a large sum, right? So you can imagine each row, the output ends up being, 1 by 10, okay? Or so here, let's, our gradient with respect to the first weight matrix is 784 by 30, right? And we would calculate this for each one row, and then basically we stack them all up. Okay, so you have something here. Okay, the output being 784 by 30, and then you have basically one for each row. And you add them all up, 60,000 to add up. And so it's a lot of computations. So what we're going to do is we're going to take all 60,000 rows, okay? 60,000 by 784, and I'm going to just kind of slice it up, all right, into a bunch of smaller things, okay? So how many of these things am I going to do? I'm going to just do batches of 10 rows. 10 by 784, and then I'm going to get another 10 by 784, and I'm going to have 6,000 of these things. So I'm going to do small batches of 10 rows at a time. Okay, so I'm going to take my 60,000 rows, split it up into 6,000 small batches. I don't know how to center the video on this. 6,000 batches of 10 rows at a time. And then I take those 10 rows, I feed it through, and that's a lot fewer calculations I have to do, right? I do, I'm taking multiply by the first weight matrix of 10 by 784, multiplied by 784 by 30, I get a 10 by 30, and then I do it by multiply by the next matrix, 30 by 10, so I get a 10 by 10. So anyway, I just have fewer calculations to do at a time, and then I'm just going to iterate over all of the different batches. Okay, so that is known as stochastic batch gradient descent, meaning we're not going to use the entire training set every single time. We're going to just do small batches of 10. And then actually I'm going to just go through the 60,000 rows just once, okay? But in groups of 10. So we're going to have like 6,000 iterations here. So I'll go ahead and do this. So I'm going to just kind of split up my data set into 6,000 batches of 10. And then here is the gradient descent part, right? And my hope is that this looks kind of familiar. I don't know. So basically I'm going to start by subsetting the data just down to the kind of 10 rows at a time. And then using those 10 rows, I do forward feed and I say, hey, do x times w1, apply the activation function, take those results, multiply by w2, apply the activation function. Those are going to be your predicted values. Okay, so that's going to be my 10 by 10 grid of predicted values. I have 10 observations. I have 10 prediction nodes. So just for this batch of 10, give me the predicted values. Once I have my predicted values, I can calculate the gradient. Okay, we have delta W3, which is y minus y hat sigmoid prime Z3. This is the structure of our network is exactly the same as what we went through when we had the very simple network with only kind of 2 nodes in the input layer, 3 nodes in the hidden layer, and 1 node in the output layer. That structure is exactly the same. It's just we have more nodes, okay? And because we use kind of the linear algebra notation or the matrix notation, I don't have to redo any calculations because all of those vectors and matrices just you can kind of expand them without having to worry about it. So all of the gradient calculations that we did still work. So I've got delta 3 dj dw2, which is a2 transpose times delta 3, delta 2, which is delta 3 times w2 transpose times sigmoid prime z2, and this. So I calculate the gradients there. And once I have the gradients, I do gradient descent, which takes my current values of w, and I subtract off a scalar multiplied by the gradient. Okay? Is that okay as far as how this goes? So this is the code that we're going to use to train our neural network. So there's nothing super unusual. My arbitrary scalar value is just going to be 1. So I could just do w1 minus the scalar times dj dw1 or whatever it is. And we'll go ahead and run that. So let me just see. Okay, so I think it'll just take a couple of seconds for me to run. So it's running and running and running, doing batches of 10, going through all 60,000 images, and now it's done. Okay? All right, so let's see how did it do, okay? Oh, I guess one thing I did do is I scaled the values by dividing everything by 255, so everything's a value between 0 and 1. Okay, so now we will go to the test data set. The test data set is 10,000 images that we have not seen, okay? 10,000 brand new images that we have not seen, but we'll go ahead and try this out. So we'll take our test data set. I'm going to just have it do forward feed, and we are going to have it guess the value. And the way we're going to have it guess the value is we're going to ask which column. Remember, the outputs are numbers between 0 and 1, and we're hoping one of these is the high. Well, we're going to ask which column has the highest value, and that's going to be the one that corresponds to our guess. And so we're going to our guess is basically going to be our maximum column, but because R is 1 index rather than 0 index, that first column corresponds to the digit 0. So whatever that column is, we're going to just subtract off 1, okay? Because we have 10 columns. The 10th column corresponds to a 9. That first column corresponds to a 0. So our guess is going to be our max column, whatever it is, minus 1. Okay, so so if I just show you what y underscore hat is, let's just look at the first, say, 6 rows. That's hard to read. Let me round that off to, say, 5 digits. Okay. So when you round it off to 5 digits, you can see this first row. We have values after we trained our network. The values are 0.00019, 0.0000, 0.00237, 0.00021. This is 0, 0, 0, 0. And then I got 0.99978. Then pretty much 0 and pretty much 0. Okay, so this first digit is what? It's predicted to be the number 7, right? Let's see, okay? And we say, okay, what was our first guess? Our first guess is the number 7. Let's see what the image looks like. We're going to ask, okay, let's look at that thing and let's plot it. And ta-da! It looks like it worked. Okay, and I think this is the the image that that we have right here. Okay, I think, is that it? It looks like it. Yeah. So that's one image from the test data set. Okay. All right. Let's try. What's the second row? So the second row we're not as confident, but the highest column is 0.88626. So and that corresponds to 012, this number 2. So our second guess is the number 2. That's the max column. And let's see what it looks like. Yep, that's the number 2. Okay. And all right, let's try the third one. It's predicting to be a number 1. That's our guess. And what does that look like? Yep, that's the number 1. Okay. So it seems like it's working. Okay. And again, there was at no point was there magic, right? Sometimes you have this neural network and it feels like you ask the computer to do something and it does something and it feels like magic, but it's not. We just said, hey, here's the matrix coming in, do these multiplications, and we get the output and we understand that process. And we said, we need to figure out the best W's to use. How are we going to figure out the best W's to use? We're going to do gradient descent. How do we do gradient descent? We calculate the gradient and subtract that off from wherever we're currently located and just do that a whole bunch of times, which is exactly what we did here. We said, we figured out how to calculate the gradients and then we updated our values. And we just said, do that a whole bunch of times. And we did it, and now we have a trained neural network. How many view quiz answers have I given you? Just one. Okay, let me give you your second one. The letter D. D as in dog. D as in dog. Okay, so I'm going to compare our performance, look at our performance and say, hey, what were the actual values versus what were our guesses? And let's create a table out of these things, comparing them. And this is the results. So when the actual value was a 0, we guessed the number 0 941 times, okay? However, when the actual value was a 0, we guessed the number 2 10 times. We guessed the number 6 21 times. All right. When the actual value was a 1, we guessed the number 1,113 times. But sometimes we guessed other numbers incorrectly. All right. And so the diagonal is when we got it right. Anything that we got off the diagonal is when we got it wrong. Okay. So we can ask, okay, what is our accuracy? I can just take the diagonal, sum of the diagonals, and divide it by 10,000. That's how many entries we have. And our simple neural network is able to accurately guess the digits around 92.5% of the time. Okay? So not great, but also not bad, right? I feel like good job, simple neural network that we created, like with my own little hands here. Okay, you know, and then let's just say, hey, you know what? Let's see what are some locations where these are like where it got it wrong. Okay, and so the 9th image in our data set, it guessed incorrectly. All right, so let's just go ahead and take a look at that. It guessed the number 5. Oh, no. The actual value is the number 5. And what did it guess? It guessed the number 6. Okay. All right. Let's see, neural network. Let's see. And we go, oh, you know what? Neural network, not your fault. Like, yeah, that is the number 5, but also that's some pretty bad handwriting. We're not like upset at the neural network for getting this wrong, right? Okay. All right, let's try out another example. Another image it got wrong was image 16. Okay. All right, and so the true label is also a number 5. This time it guessed the number 3. Oh, that seems a little weird. And we go, okay, yeah, you know, you probably should have gotten that one right. Okay, you probably should have gotten that one right. But you can kind of go through and just kind of see like some of these labels. I'm going to just arbitrarily pick one, 8,273. And let's see, what is the label? The true value is a 3. It guessed the number 5. Man, are 3s and 5 hard to tell apart? Let's see that. Yeah, okay, all right. I guess I kind of see it. That's definitely the number 3. But also, there are some elements that look kind of 5-ish about it, right? A little bit. So these are the ones where the network got it wrong, and certainly probably with some better design choices and other things that you can do, you would get better results. But also, like I don't know, it's kind of neat as far as running this code. So all of this code is posted on Brew and Learn, and you can kind of download. You'll have to download the MNIST handwritten digits data set, and you can do that. And so the performance of the neural networks have improved dramatically over time. Where 92% wouldn't be good anymore, but pretty much all of our image recognition stuff that's happening today, where you take a picture on your phone and then later on you ask it, hey, give me pictures of my cat or whatever, and it's able to do this. That's basically just a more complicated or just a bigger neural network going on that's been kind of trained a little bit more sophisticated. But anyway, this is just we're just scratching the surface here on neural networks. This concludes our section on neural nets. We'll kind of return back to textbook stuff. But I thought this was kind of a neat, fun little application of gradient descent, and it's kind of just fun to see how this stuff works. Okay, so we'll wrap it up here. I guess your next homework assignment, you'll do some neural network stuff. You have to do some gradient calculations for the bias matrices, and so that's in your homework. Okay, we'll wrap it up. So have a great rest of your day. If you're at DataFest, enjoy. I'll see you on Saturday. I'll be there to I don't know, I guess walk around, answer questions if you have them. And other than that, yeah, have a great weekend. And I will give viewers here, or the people here, the third view quiz answer.